Hey, astronomy students. This is Mr. Lark. Okay, let's finish up talking about these death of stars by talking about the death of massive stars. Because we talked about the smaller ones. They become white dwarfs. Whoopee, right? Not exciting at all. Okay, but what happens to those bigger ones? Well, let's talk about binary stars, because typically you're going to find those bigger ones when you have a binary star system. And in a binary star system, you have two stars that orbit each other around a central location or central point, right? Well, when they orbit each other, they control two regions of space called Roche lobes or Roche surfaces. Okay, so Roche surfaces is this big area that kind of forms a teardrop shape around the planet. And then this one has a teenier one because, well, it's a teenier planet, right? Okay, or star, excuse me, not planet. My bad. All right, well, these Roche surfaces also have points around them in this binary system that are called Lagrangian points. And Lagrangian points mark places of stability where matter can remain without being pulled towards one of the stars. And the mass is actually able to flow back and forth from one star to the other through this inner Lagrangian point right here, which happens to be I guess I would consider that to be the center of orbit. Okay, so here you have the two outside Lagrangian points, the L2 and the L3. It's stable if it's a certain way, but if it's something, and I can't remember exactly what it is, but if something happens, that matter can actually be just whisked away very quickly. Okay, and then you have these other two Lagrangian points here. But this Lagrangian point here, number one, this inner Lagrangian point, is where that matter can actually be pulled from one star to the other. Let's see. Closed binary stars can transfer mass from one star to the other, and it'll result in a main sequence star that's actually going to be more massive than the giant companion star, and this is known as the Algol paradox. Oh, I had all that on here. Sorry. I forget sometimes. Okay. Let's see. Mass can also be mass transfer in a binary system can significantly alter the star's masses and affect their stellar evolution, which is pretty much what I said there with, here, let's see. Okay, so star B here is more massive than star A, but mass is transferred from star B to star A through the Lagrangian point here, this inner one. They actually end up becoming similar in size, but it's still pulling, and this star A ends up becoming the more massive star, but it's actually a giant. Okay, and star B is going to be what was the mainstream, or the main sequence is now actually going to become a white dwarf. Okay, so they pull, and it changes, well, pretty much what they're going to be. Let's see. Mass can be transferred from an evolving star through an accretion disk that happens around the receiving star. And the accretion disk can become hot enough to emit light and X-ray radiation. Okay, so binary systems consisting of a white dwarf and a main sequence or red giant star. You can end up with white dwarf accretion disks where it pulls the matter from the companion star or the other star, and angular momentum is conserved, and that's where the accretion, the matter is pulled into this disk, and that's how it makes that accretion disk, because if it spins faster and faster, it flattens out. All right, matter in the accretion disk heats up to about 1 million Kelvin, and it can give off X-ray emissions, it can give off X-ray emissions and light. Here we go. All right, so nova explosions. What are nova explosions? Well, nova explosions is what happens when mass is transferred onto the surface of a white dwarf. Okay, so how can it transfer to the surface of a white dwarf? Well, hydrogen that's accreted through the accretion disk can accumulate on the surface of the white dwarf. So it's being pulled from the other star, and the hydrogen just kind of builds up on the surface of the white dwarf. Okay, this becomes extremely hot, and a dense layer of the hydrogen that's not going to fuse, and it's just sitting on the surface, and it ends up exploding or going up in flames, right? it explodes and erupts in a nova explosion, and it can happen repeatedly as long as that mass transfer continues. Pretty cool, huh? All right. In many cases, the mass transfer, like I just said, can happen repeatedly. Okay, that's pretty much what it's saying. Okay, the fate of our sun. So what's going to happen to our sun and what's going to happen to the Earth? So the sun's going to expand to a red giant in about 5 billion years. It'll expand to where it's about where the Earth's orbit is. So it's going to get really, really, really big. The Earth probably won't exist anymore. It'll either be incinerated or it will still exist as a planet because it'll come straight to the outside of our orbit or to the inside of our orbit, but it won't look like Earth anymore. The sun, the oceans will be dried up. Any viable life will be gone. It'll be desolate terrain. The sun may form a planet nebula, but they're still uncertain on that. And they said that the leftover core will become a white dwarf. Okay. Let's see. Lives of massive stars. So let's talk about massive stars. Massive stars are going to be anything that is 8 solar masses or greater, and they live very short and very violent lives. Very violent lives. All right. So what happens to the death of a massive star? Stars that are more massive than 8 solar masses cannot lose mass fast enough to reduce their mass so that it's low enough to die by ejecting a planetary nebula and collapsing into a white dwarf. So it's not going to become a planetary nebula, and it's not going to become a white dwarf. Well, what happens? Well, the massive stars will fuse hydrogen to form helium, which fuses to form carbon, and oxygen, which fuses to form neon, which fuses to form silicon, and that fuses to form iron. Iron is kind of like the dead end. It doesn't go any further than that. Okay? It stops when it gets to iron. Iron is, well, the dead end. Okay, when the star has an iron core, it can't burn off anything else, and it's going to actually end up collapsing on itself, and it triggers a supernova explosion. Okay, so it has the iron core on the inside, and then you have your silicon on the outside next, and all these layers. It continues to fuse and fuse and fuse until there's so much iron in here that it becomes so heavy there's no gas to build up the pressure to hold it up, and so it just kind of collapses on itself and it becomes a supernova. And that's just another example of what it looks like. All right, so observations of supernova. You can see them easily in distant galaxies. Okay, and there are 2 different types of supernova. There's a type 1, and the type 1 has no hydrogen lines in its spectra whatsoever. And then in the type 1, you can have 2 type 1s. You can have a 1A, which occurs when mass is transferred onto a white dwarf that pushes that white dwarf over the Chandrasekhar limit, over 1.4 solar masses, and it collapses suddenly, fusing all of the carbon at once. And then you can also have a 1B, which occurs when a massive star loses its outer layer of hydrogen in a binary system. Okay, gives all of its outer hydrogen to the other star in the system. Its iron core collapses and it explodes as a supernova. It's so much fun, it explodes, right? Okay, type 2 supernova, you can tell it's a type 2 because it has hydrogen lines in it. Type 1, no hydrogen lines. Type 2 does have hydrogen lines. Sorry. There we go. I knew it was on here somewhere. All right, supernova remnants. So the Crab Nebula is an example of a remnant of a supernova that was observed in 1054 AD. What is a supernova? Oh, let's go back. What is a supernova? Well, expanding expanding shells of gas is ejected by supernova explosions, and this is filled with hot gas. These expanding shells, they're filled with hot gas. And the shocks of a supernova remnant can shoot off protons and electrons at extremely high energies. These are known as cosmic rays. And in magnetic fields, these electrons that it's giving off can emit synchrotron radiation. All right, so more remnants. The Cygnus Loop and the Veil Nebula are both supernova remnants. And we have Cassiopeia. And this is seen in visual or optical, and then this is the same one in X-ray. All right, so what I was saying is that in these supernova explosions, they can give off photons. Hopefully I didn't write protons on the notes. If I did, I apologize. I did fix it. It shoots off photons and electrons at extremely high energies. These are cosmic rays. Okay, and oh, it is protons. Sorry, I did that right. And in magnetic fields, these will emit this radiation. Okay, so there was a famous supernova of 1987. Until 1987, scientists had never really been able to observe a supernova explosion. There were ones that were in the past that they had heard about, but recent scientists weren't able to actually observe anything. So it's believed to have been produced by a Type 2 supernova in the Large Magellanic Cloud in February of 1987. They also said that this is before and this was the after, so you could actually look at it and, ooh, it's teeny tiny, oh, it's huge. Okay. Neutrinos were detected, and they are actually evidence that the iron core collapsed and presumably formed a neutron star. Okay, so what happened? Well, it exploded. Here's the supernova. Whoop. Here's the remains of it, and they think that it actually formed a neutron star. We're going to get into neutron stars soon, and the resulting nebula is actually still developing to this day, right? Because here's from 1987, and this one here is from 2004. Here's a shock wave that's expanding into the ring of gas that's going around, and this is what remains of the star. All right, so local supernova and life on Earth. Nearby supernova could kill many life forms on Earth through gamma radiation and high energy particles. That would not be good. At this time, thank goodness, no star capable of producing a supernova is within 50 light years of us. Okay, thank goodness. Most massive star that we know of is about 25,000 light years away from Earth. Yay, we're not going to die from a supernova exploding. Woo! All right, and I just had to, because we're talking about death of stars, I had to put it in here. So I'll see you in class.